Hello and welcome to this episode of our series NASA Biology on Earth and in Space. In our last show, Earth's atmosphere was discussed. In today's program, we will hear how carbon dioxide in the Earth's atmosphere may become a major economic and environmental problem. Research scientist Dr. James Casting from the NASA Ames Research Center tells us about the carbon dioxide cycle and how it influences life on our planet.
Well, I'd have to say that the carbon dioxide cycle is generally misunderstood at most levels, including some of the highest research levels, because there is so much that goes on into controlling the levels of carbon dioxide in the atmosphere. Most of the current interest in CO2 is focused on the changes in CO2 that are occurring right at this time in our history, and that is due to the burning of fossil fuels, or at least largely due to the burning of fossil fuels. And you can read about it in the papers. There's a lot of interest because the current increase in CO2 is thought to be contributing to, or will be contributing to, an enhanced greenhouse effect, and therefore the global temperatures on the Earth are likely to rise over the next 50 to 100 years. The CO2 happens to be a very interesting gas because the control mechanisms are rather complex, and they occur on a variety of different time scales, so that on very long time scales there may be one mechanism which controls CO2 levels, whereas on shorter time scales the control is exerted by a totally different type of mechanism. So what I hope to do in this presentation is to go over the natural controls on CO2, starting off with the very longest time scales, the billions of year time scales during which the Earth has evolved, and then I'm going to work my way up through the 100 million year time scale, going back to the Cretaceous period when the dinosaurs were roaming around the Earth, and then up to a relatively recent time scale of the Pleistocene ice ages, which have been occurring with regularity over the past couple of million years, and then finally say just a couple of words about the fossil fuel problem, which hopefully will be placed in somewhat of a better perspective by going over the history of CO2 on these other time scales. So what I'd like to do is start out with the very longest time periods. The Earth was formed 4.5 billion years ago, and as I've shown in my first slide, there have been a number of changes in the Earth's environment that have been important on that time scale. One of the most important of which is the fact that the sun's output has changed over the past 4.5 billion years. This is not something that's unique for the sun. This happens to all main sequence stars. Almost all theories of the sun's evolution agree that the sun has to increase in output as it ages. So the implications of this for climate were first pointed out back in 1972 in a paper by Carl Sagan and George Mullen, where they showed that all other things being equal, that is, if the composition of the Earth's atmosphere had not changed during the past 4.5 billion years, the Earth's surface should have been completely frozen over prior to about 2.3 billion years ago. That is, the oceans would have been frozen and complete glaciation. So this is at odds with what we know from the geologic record. There's very good geologic evidence for the existence of running water back to the earliest known rock record, 3.8 billion years ago. And in fact, there's no evidence that there was any glaciation whatsoever until 2.5 billion years ago, the so-called Huronian glaciation. Now the question is, could the Earth really have had CO2 levels that were 1,000 times higher than today? The answer to that question is yes. The Earth has lots of CO2. In fact, the amount in the atmosphere is really a trivial fraction of the Earth's total carbon inventory. There's currently about 60 times the amount of CO2 that's in the atmosphere, which is dissolved in the ocean as carbonate and bicarbonate ions. And even that is only a small fraction of the carbon. Most of the carbon actually exists as carbonate rocks in sediments. And if you took the total amount of carbon in carbonate rocks and put it all into the atmosphere as CO2, you'd end up with an atmosphere which would look very much like the atmosphere of Venus. which has about 90 bars of carbon dioxide in its atmosphere. Earth has 1 bar of carbon dioxide. A bar is the total surface pressure on the present Earth. So that would be an atmosphere 90 times as thick as the Earth's present atmosphere, but composed entirely of CO2. If you put even a small fraction, to get 1,000 times the present CO2 level, we're talking about a few tenths of a bar of CO2, clearly a small fraction of the Earth's total carbon. And the question is, how do you decide how much carbon was tied up in the carbonate rocks back in the past and how much was in the atmosphere and in the ocean? Well, the first thing to notice is that the atmosphere and the ocean are linked in the sense that CO2 can dissolve out of the ocean or can redissolve in the ocean. And on long time scales, the atmosphere and the ocean tend to stay in equilibrium. By long time scales, you're really controlled by how fast the ocean can turn over and expose new surface water to the atmosphere. And it turns out that it takes about 1,000 years for the ocean to do that. So that on any time scale longer than 1,000 years, the atmosphere and ocean stay in equilibrium, and what you're really interested in is the total amount of carbon dioxide in the atmosphere-ocean system versus the total amount of carbon dioxide in the carbonate rock reservoir. Well, to determine the relationship between those two, you have to look at the so-called rock cycle, which is also referred to as the carbonate-silicate geochemical cycle. Well, this sounds complicated, but in fact, it's not all that complex. And I have here a slide that illustrates this thing schematically with just 2 simple chemical reactions. The first is what's called the silicate weathering reaction, in which you start with calcium carbonate or calcium silicate, CaSiO3, combine that with atmospheric CO2, and end up with calcium carbonate plus silica, SiO2. This actually happens in liquid water solution. You need rainfall and precipitation, and you weather, or that is erode and chemically react rocks on the continents, release these minerals, silicate minerals, into the rainwater, and then that water containing dissolved minerals and carbon dioxide, which once it dissolves is in the form of bicarbonate ions. That water washes down into the oceans, filling up the oceans with calcium ions and with bicarbonate ions. Then in the oceans, the calcium and bicarbonate get together, precipitate out as calcium carbonate, and go down and form sediments on the floor of the ocean. This is accomplished today in the present oceans by the activities of biological organisms, plankton in particular, who form their shells out of calcium carbonate. On the early Earth, that was probably not the case, but in fact you can form calcium carbonate inorganically as well, as if you just allow the calcium or bicarbonate concentrations to achieve higher levels. Well, that is the loss mechanism for CO2 from the atmosphere-ocean system, because you're in this process, you're taking CO2 out of the atmosphere and you're putting it into the sediments as calcium carbonate. What happens to these sediments, though, is that the carbon is not lost irrevocably. In fact, these sediments are on the ocean floor, but as we all know, the ocean floor is not a static platform. Because of plate tectonics, the ocean floor is constantly moving. In fact, ocean floor is constantly being created at the mid-ocean ridges, the centers of the oceans, and then it spreads out gradually towards the continental margins. And at the continental margins, it gets subducted back down. Well, when that happens, the carbonate sediments that are on the ocean floor get brought back down to higher temperatures and pressures within the Earth's crust and going down into the mantle. And at higher temperatures and pressures, just the reverse of the weathering reaction occurs. And this is the second reaction shown on the slide. And it's referred to as silicate reconstitution or carbonate metamorphism. And what happens here is that calcium carbonate from the sediments recombines with silica, which also is contained in the sediments, to reform calcium silicate plus CO2. And the CO2 bubbles back into the atmosphere through volcanoes and through other cracks in the Earth's surface. So that in the very long term, this is the restoring mechanism by which CO2 re-enters the atmosphere-ocean system. If you didn't have this mechanism occurring, then the atmosphere would become depleted in CO2 in a very short time scale, and the greenhouse effect would go away, and in fact the Earth would get very cold. Well, understanding this cycle is the key to understanding how the Earth's atmosphere could have had very high CO2 levels in the past. Well, at any rate, the best explanation for why carbon dioxide levels could have been higher on the early Earth has to do with the fact that if the Earth had been much colder than today, then the silicate weathering process would have gone more slowly, and therefore the loss process for CO2 would have decreased, and CO2 levels would have naturally built up in the atmosphere. So that probably the Earth never did freeze over, almost certainly the Earth never did freeze over entirely, but in fact there was a natural feedback mechanism that provided climatic stability by enhancing the amount of CO2 in the early atmosphere. Well, this same rock cycle that controls the carbon dioxide concentration of the atmosphere on very long, billions of year time scales can also operate on shorter time scales. In particular, there's some evidence now that CO2 levels may have been significantly enhanced during the Cretaceous period, which is the time about roughly 100 million years ago when the dinosaurs were roaming the Earth. We know from the climatic record that, in fact, the Cretaceous period was a very warm period in Earth history, and that the globally average surface temperature during the Cretaceous was probably about 10 degrees centigrade warmer than the present global temperature. Well, there are several possible reasons why it could have been warm during the Cretaceous, one of which is that the continents were in different positions. In particular, they were more clustered towards the equator. There was less continental area near the poles on which ice caps could accumulate. So, in fact, this is a very likely explanation for part of the temperature increase during the Cretaceous, and the best climate models that have been run indicate that you can account for roughly half of that 10-degree global warming by just simply moving the continents around to different positions. But, in fact, that still leaves about 5 degrees to be accounted for, and the interesting thing that has come out just in the last couple of years is that it's very likely that that other 5 degrees of warming was accounted for by higher CO2 levels in the Cretaceous atmosphere. The reason for this is that the rock cycle was probably operating faster, essentially, during the Cretaceous than it is now. The evidence for this being the fact that the seafloor spreading rate, the rate at which the seafloor is created at the mid-ocean ridges and moves towards the continental margins, can be measured by looking at magnetic anomalies in the ocean floor. Magnetic anomalies are merely the signature which is left when the Earth's magnetic field reverses, as it does every few thousand years on sort of a random basis. Anyway, by looking at these magnetic anomalies, we can estimate how fast the ocean floor was spreading. And the estimates disagree numerically as to what the change was, but they do all agree that spreading rates were significantly higher back around 100 million years ago. So if you think of that in terms of the carbonate cycle, the carbonate sediments that are on the ocean floor would have been brought to the continental margins and subducted and metamorphosed more quickly at that time than they are today. So that should give you a significantly enhanced CO2 production rate during the Cretaceous. And in fact, people have now tried to make rather elaborate geochemical models of the CO2 cycle to see what effect that would have on atmospheric CO2. It is now possible to measure CO2 in ice cores that are taken from Antarctica and from Greenland. And these ice cores can be dated back to 30 or 40,000 years by just simply looking at the annual layers of ice and counting layers. Within these ice cores are little air bubbles that were trapped during the formation of the ice and which have maintained the composition of the atmosphere in which they were from which they formed. And now measurements by a number of different groups have shown that in fact during the last ice age, that is prior to about 11,000 years ago, the CO2 concentration of the atmosphere was about 200 parts per million, and then it suddenly jumped up to about 250 parts per million right at the close of the last ice age. Well, this is very interesting because, of course, climatologically, if you get a CO2 increase, that should give you a global warming, and the question now is, could this CO2 increase explain could that possibly be the reason that we popped out of the last ice age? And second of all, what could possibly be causing CO2 to change dramatically in such a short time scale? Well, the answer is probably has to do with the biological productivity in the surface ocean. And this is something that is not normally thought about, but if you make a simple two-box model of the ocean, that is, divide the ocean up into a surface layer which contains most of the biology, the species which are performing photosynthesis, and then a deep ocean which contains the rest of the water in the oceans, you find out that the concentration of, and observations show that this is true, the concentration of dissolved CO2 in surface water is significantly different than it is in deep water. The reason being that organisms are constantly taking CO2 out of surface water and incorporating it into their bodies as organic matter and as carbonate, into their shells as carbonate. Then as these organisms die, they fall down into the deep ocean. Most of the organic matter is reoxidized, and much of the carbonate redissolves into the ocean. So the net effect is that you have a biological pump which pumps carbon from the surface ocean to the deep ocean. We now have been monitoring CO2 levels very accurately at the Mauna Loa Observatory in Hawaii ever since 1958. And in fact, CO2 has been increasing constantly since that time, although there's a slow increase. It's gone up from about 315 parts per million in '58 to about 340 parts per million today. Superimposed on this slow increase is a 5 or 6 part per million wiggle, which is due to the photosynthetic cycle on the continents, in particular in the northern hemisphere. But nevertheless, this increase in CO2 is thought to be due primarily to burning of fossil fuels. And if one takes all of the fossil fuels which have been burned since the late 1800s, if about 50% of that carbon is going into the atmosphere, then that is enough to explain the observed CO2 increase. That is the current theory, and it's likely that we're going to continue burning carbon dioxide, that carbon dioxide levels will continue to increase, and in fact, the best estimates are that CO2 levels will approximately triple over the next 200 years. If CO2 levels triple, then the Earth's surface should warm up by 4 or 5 degrees centigrade during that time, which will make the Earth warmer than it has been at any time since the late Cretaceous. This has now been predicted in reports by both the National Academy of Sciences and the Environmental Protection Agency, and in fact, it's something that we should probably look forward to in our future. The greenhouse effect is basically due to the fact that CO2 and water vapor, for that matter, both are fairly transparent to visible radiation. And most of the sun's energy comes to the Earth in the form of visible radiation, just light that we see. On the other hand, the Earth radiates back most of this energy as infrared energy or heat, and both CO2 and water absorb infrared energy very well. Therefore, they let the sunlight in, but trap the outgoing infrared radiation. The reason is kind of counterintuitive, but you don't hear much about the greenhouse effect of water. Water is actually a much better greenhouse gas than is CO2. It absorbs throughout much of the infrared spectrum, whereas CO2, really the absorption is more concentrated in specific areas. However, water is controlled water can condense out of the atmosphere, and therefore it's controlled very much by its saturation vapor pressure. So what actually happens in terms of the climate is that CO2 can be thought of as a driver mechanism. If you increase CO2, you increase surface temperature by increasing the greenhouse effect. That evaporates more water, and the water amplifies the effect of CO2, so that the greenhouse effect is due to both gases, but CO2 is the one that you're more worried about from a climatic standpoint. One of the most productive ways of looking at the carbon cycle, I think, is to compare Venus and Earth and Mars and try to see why they each evolved so differently. Venus has in fact, both Venus and Mars have predominantly CO2 atmospheres. There's a big difference in pressure, though. Venus has a surface pressure of about 93 bars. That is 93 times the surface pressure on the Earth. Most of that, about 97% of that, is CO2. Mars, on the other hand, is again about 96 or 97% CO2, but the surface pressure is only 6 millibars, or 6 1,000ths of the surface pressure on the Earth. So that here we've got vast differences in the total amount of carbon as carbon dioxide on in these atmospheres. Now, you ask why do we see such great discrepancies between the planets? Well, let's take Mars, case of Mars first. Mars, in the first place, we don't know for sure if Mars was ever endowed with as much carbon dioxide as the Earth was. But even if it was given a large CO2 atmosphere, and I should say that there is some evidence for it, in that there is evidence for running water in the past on Mars. There are channels that were very obviously formed by running water, and which probably could only have been formed by precipitation from a relatively warm, dense atmosphere. The most likely explanation for primitive Mars, just as it is for primitive Earth, is that you had a dense carbon dioxide atmosphere producing a big greenhouse effect, and that allowed liquid water to exist and to form those channels. Well, now, Mars had a problem, though, and that was that Mars is significantly smaller than the Earth. And small objects tend to lose their heat. They cool off much more rapidly than big objects do. And it's the internal heat of the Earth that keeps plate tectonics going, and it's plate tectonics that keeps carbon cycling through the CO2 geochemical cycle. Well, on Mars, it was too small. Very early in its history, plate tectonics ceased, if indeed it ever operated in the first place, and Mars was unable to recycle carbon dioxide the way that the Earth does. So if you had liquid water there, which there is evidence for it occurring, you should have formed carbonates and subtracted CO2 from the atmosphere, but you weren't adding it as you were in the case of the Earth. So the process was essentially irreversible, and Mars, the atmosphere became thinner and thinner, and the climate became cooler and cooler. Now, Venus, and finally, it would be very interesting to consider what would be the case if Mars was the same distance that it is now from the Sun, but if it was the same size as the Earth. Well, then the same process, and had the same carbon dioxide endowment, then the same process which we think kept the early Earth warm ought to be keeping Mars warm today. You would in fact expect, for instance, if you took the Earth and put it at Mars's orbit, you would in fact predict, or at least I would predict, that the climate should be much warmer than the present Mars. In fact, you should have an average surface temperature which is warm enough to allow liquid water to exist, and that you should have a dense CO2 atmosphere which is maintained by the carbon cycle. Because the analogy to the Earth is that you have to have liquid water in order to keep the carbon cycle in balance. So Mars's problem is not that it's too far out, basically, but that it's too small. Now, if you go to Venus, the problem is different. Venus is the same size as the Earth, so from the tectonic standpoint, one would expect that it should be possible to recycle carbonates. And in fact, Venus has the opposite problem from Mars. It's got a huge dense CO2 atmosphere instead of a relatively thin atmosphere. Well, what happened to Venus? The answer is the obvious, again, which is that Venus was too close to the sun. I think that the key issue 50 to 100 years in the future is going to be carbon dioxide. I think that we're just seeing the beginning of this CO2 as a climatic problem. It already gets a lot of press, but in fact, even though CO2 levels have been observed to go up, we have never seen the climatic effect of CO2. During that, say, next 100 years or so, the sea level may begin to rise by a meter or two. Now, that again doesn't sound like that much, but in fact, that would flood significant areas of coastal real estate. And economically, that would have very severe consequences. And I think when we begin to notice a problem, an environmental problem, is when it really begins to hit us in the pocketbooks. And I think that all the scientific evidence indicates that CO2 is going to be a big economic environmental problem and much bigger 50 years from now than it is today.
Each year we learn more about the planet in which we live. As tenants of this planet, we have the responsibility to use this knowledge to provide for a better world for the generations to come. Through its various research activities, NASA will strive to achieve this goal. Thank you for joining us. This is Lynn Bondurant saying goodbye from the NASA Lewis Research Center, Cleveland.